Welcome back to In Parts 1 and 2, we explored what black holes are, how they form, and the different types, from stellar to supermassive. But black holes are not just massive, they're bizarre. They bend time, warp light, and create phenomena that seem straight out of science fiction. In this episode, we'll explore time dilation near black holes, the event horizon and singularity, black hole information paradox, black hole versus white hole, do black holes die? Hawking radiation explained, future research and mysteries. By the end, you'll see why black holes are the ultimate cosmic puzzle and why physicists are obsessed with them. First, let's revisit the event horizon, the invisible boundary of a black hole. Cross it, and escape is impossible, not because of suction, but because gravity is so strong that even light cannot escape. Inside lies the singularity, a point of infinite density. Here, the known laws of physics break down. Space and time as we understand them cease to exist. And this is where black holes get truly mysterious, because everything that falls in is compressed to an unimaginable degree. General relativity describes how mass curves space-time, but at the singularity, it predicts infinities, which means our current physics can't explain it. That's why black holes are a playground for theorists seeking a quantum gravity theory. Now for one of the most mind-bending effects, time dilation. According to gravity affects time. The stronger the gravity, the slower time moves. Near a black hole, time passes much more slowly than far away. For example, if you were orbiting close to a supermassive black hole for a few hours, centuries could pass in the rest of the universe. This is not just theory. Time dilation has been observed near massive objects like neutron stars and is predicted by relativity. Near the event horizon, the effect becomes extreme. Imagine a what-if. Astronauts orbiting close to a black hole return to Earth and find everyone they knew long gone, as decades or centuries have passed. This isn't science fiction. It's a direct consequence of the physics of black holes. Black holes also warp light in fascinating ways. The gravity of a black hole bends light from stars and galaxies behind it. This phenomenon, called gravitational lensing, can magnify distant objects and even create multiple images of the same galaxy. Around a black hole, the effect is extreme. The light from the far side of an accretion disk can wrap around the black hole, making it appear to float above and below the event horizon. This is exactly what astronomers captured in the first image of M87's black hole. Even photons, the fastest particles in the universe, can get trapped in orbits around a black hole, creating a photon sphere, a halo of light that circles the event horizon. Some theories propose the existence of white holes, the opposite of black holes. While black holes trap matter and light, white holes theoretically eject matter and energy. White holes are purely theoretical. They haven't been observed. But some scientists suggest that black holes and white holes might be linked, possibly through wormholes or alternate regions of spacetime. Even though white holes sound like science fiction, exploring these ideas pushes our understanding of the universe and quantum physics. One of the most debated mysteries in physics is the black hole information paradox. Here's the question: when something falls into a black hole, is the information about that object destroyed forever? According to quantum mechanics, information can never be lost. But if a black hole eventually evaporates, what happens to that information? Stephen Hawking proposed that black holes emit radiation, now called Hawking radiation, and could eventually evaporate completely. But does this radiation carry information, or is it lost forever? This paradox is still unsolved, and solving it could unite quantum mechanics and general relativity, creating a theory of quantum gravity. Let's dive into Hawking radiation. Even black holes aren't eternal. Stephen Hawking theorized that black holes emit tiny amounts of radiation due to quantum effects near the event horizon. Over trillions of years, this radiation could cause a black hole to evaporate completely. Smaller black holes evaporate faster than supermassive ones. So yes, in theory, black holes can die, but it would take longer than the current age of the universe for most to vanish. This idea transformed black holes from being purely destructive to something that interacts with the universe in subtle ways. Here's the ultimate mystery: what happens inside a black hole? We can't see inside, and no information escapes, but scientists use simulations and theory to make predictions. Matter is crushed into the singularity, gravity becomes infinite, and time may cease to exist as we know it. Some theories suggest exotic states of matter could form, and some quantum gravity models even propose that black holes could connect to other regions of space or even other universes. But these are highly speculative. What we do know: black holes are laboratories for extreme physics where gravity, quantum mechanics, and relativity collide. Black holes are still one of the hottest topics in astronomy. Observatories like James Space Telescope, JWST, detecting accretion disks and distant quasars. Event Horizon Telescope, EHT, imaging supermassive black holes. LIGO and Virgo, detecting gravitational waves from mergers, are giving us unprecedented insight into these cosmic giants. Simulations and AI models are helping scientists predict accretion disk behavior, jet formation, and even the outcomes of black hole collisions. Each discovery brings us closer to understanding the fundamental laws of the universe. Now for a what if. What if you fell into a black hole? Approaching the event horizon, you'd experience extreme time dilation, seeing the outside universe speed up. Tidal forces would stretch you into spaghetti. Crossing the singularity, physics as we know it breaks down entirely. We can theorize, simulate, and imagine, but no one has or will survive the journey. Yet, studying these extreme conditions allows scientists to test quantum mechanics and general relativity in ways impossible on Earth. Let's wrap up what we've discovered in Part 3. Event horizons and singularities define black holes and challenge our understanding of physics. Time dilation near black holes warps reality and illustrates relativity in extreme conditions. Black hole information paradox and Hawking radiation hint at the unification of quantum mechanics and gravity. Simulations, telescopes, and gravitational wave detectors are uncovering secrets about black holes, mergers, and jets. Black holes aren't just invisible voids. They're cosmic laboratories, revealing the very fabric of the universe. And while they're mysterious, dangerous, and mind-bending, studying them might one day answer the biggest questions about space, time, and existence itself. If you've been blown away by the strange, mind-bending world of black holes, hit like, share this video with friends who love space, and subscribe to never miss our cosmic adventures. And here's a question for you. If you had the chance, would you explore a black hole to unlock its secrets? Or is some knowledge too dangerous to pursue? Let me know in the comments.